Welcome back to the workshop. We're going to do another presentation on input-output interfaces. RSLogix, specifically the 1756 I/O, is an order of magnitude more convoluted, more complicated, more capable than the active backplane I/O for SLC500, PLC5, MicroLogix, etc. Each 1756 module of any type that slides into the backplane has a second generation RISC processor, reduced instruction set, CPU, and it does communications on its own. So the backplane, 1756 backplane, is a 32-bit parallel network. It's as if you had a 32-wire cable plugged into each module on the backplane. So the backplane is actually passive in that it's not activated. In other words, SLC500, MicroLogix, PLC5, they activate the modules one at a time and do that when they're doing the I/O scan. RSLogix doesn't do that. So each I/O module for RSLogix is much more involved and more capable. So here we have another presentation on I/O. In this recording, we're going to do more I/O, input-output configuration. In this case, we are actually moving backwards in the manual towards the beginning. We had a section titled Correlating Your I/O with the I/O used in these manuals. At the time, if you did read through this, we told you that you wouldn't necessarily understand all this right now, but you may want to revert back to these pages when it comes time for you to create the I/O structure that you're going to use for the rest of these manuals. At this point, if you have CompactLogix, it would behoove you to get an IQ6XOW4. You can find them on eBay for as little as $50. I wouldn't buy a brand new one. I wouldn't pay more than $100. But for the amount of effort, it's probably would be a good thing to pick up an IQ6XOW4. Now in the manual, and roughly page 5, 6, or 7, we had you open up the controller tags and look at the local 1 input data and then the local 1O or output data. And we stated that these two single integers, see, SINT, single integer, made up of Boolean, it's 8 bits for inputs and 8 bits for outputs. However, you can't use all 8 and 8. Your actual I/O locations are going to be 0 through 5 for inputs and 0 through 3 for outputs. That's what we showed you in the manual. And then we said that if you didn't have this IQ6XOW4, then you might have something like this. Here we have another project that has an IQ16 and an OW16, and if we open up the controller tags, you'll see this is the input data, 16 bits, and this is the output data, 16 bits. Now this isn't like RSLogix 1756 I/O, where your data words are dense and have 32 bits, even though you only have 16 actual inputs and 16 outputs. They're still made up of a dent, and the other bits are hanging out in the breeze. They're just unused. In this case, all 16 of these are available for this kind of a module. However, in our labs, you're only going to use 0 through 5 for the inputs and 0 through 3 for the outputs. Now, it is possible, if you have the digital field device simulator that we sell as part of our training collateral, that you could connect up 2 more outputs. So you have 0 through 5 or 6 outputs and 0 through 5, 6 inputs. Now the lab projects won't use those 2 additional outputs, But we always encourage our students, our learners, our friends to go beyond what the manual has you do and experiment. Make the code more complicated, make it simpler. You may have this configuration. These modules are in slot 1 and slot 2. Let's collapse this back down, and let's say that we decided to put all this input card. We'll go to properties and we'll put it in slot 6. And let's say the output card is going to go into slot 3. Now look, see, it shows 3 and 6 here. Look at the difference in the tags. Well, the only real difference is that one number right there, the slot number. We pointed that out in the lab procedure, that you may have to substitute your slot number for our logic, which looks like this. All of ours are slot 1 because it's one module in slot 1. In the manual, we also talked about creating look like or looks like tags. For that purpose, I mean, if you have this, well, you're all set, because this structure matches what we use in the manual. But if you have this, it doesn't match. As a matter of fact, we'll just leave this 6 and 3, slot 6 and slot 3, even though in the manual we show it in slot 2 and slot 3. Really doesn't matter what slot number it's in to create these look like tags. What we had you do in the controller tag database, that's this one, not program tags. If we go down to main program here, double click on program tags, see there's no tags in there yet. We're doing this in the controller tags, and you don't want to be in monitor tags, you want to be in edit tags. So we had you go to the first open field and type in local _1 _ I _ data. 1 for slot number, I for data, or the type of data, input data, then data. And then we had you create that as a single integer. There's a reason for that, because we want it to look a lot like the IQ6X-OW4. We could do it this way. When you highlight this, you could type in SI, there it is right there, then hit enter. Okay? And then we had you create another one, local 1 for slot 1 _ data, O _, and make that also a single integer, SI, enter. And in this case, you're using 1 for your input instead of 6. You're using 1 for output instead of 3. So now here's what you're going to do. In that lab project, around page 9, 10 or so, we had you expand these elements. So here's your input. Okay. Now this is 16 bits, but we only are going to use the first 6, 0 through 5, but we're trying to make this look like this one, where you have just a single integer. 8 bits for inputs, 8 bits for outputs. That's why in this project we use single integers, even though we're going to alias them to the real addresses that you have. You're going to make it look like they match these addresses over here, local 1I data. See? Local 1I data. I had you compare the tag names. Pay close attention to this next step because we're going to make the connection. So what I'm going to do is I'm going to alias, and I'm going to pick my inputs, and I'm going to pick my data word. I have these 16 bits here. It looks like it changed it to a single integer, or changed it to an integer. So watch what happens when I do this. This was originally created as a single integer, but because I'm aliasing this to a 16-bit word, which is an integer, watch what happens. So we'll go to output. Watch right here, single integer. Okay, we're going to alias this tag that looks like this tag. We're going to alias that to the actual I/O that you have that doesn't match what we're using in the manual. So I'm going to go here. Remember, this is the input, so I pick 6 I data. I'm going to pick the whole word. Okay. Now, that made this an integer. We'll make this a single integer again to see if it sticks. Now we'll go do the same thing, only for the output. So we go to 3. See, it forced it to be integers, even though I originally made them single integers. That's fine. So here's what we have now. We have local 1 I data 0 through whatever, and for the card used in the manual, we have local 1 I data whatever. The only difference are the delimiters. Here you've got colons and a decimal point. Now we could go a little bit further in making this looks like, but for right now this will suffice. So here we've created 2 tags. There's our outputs and there's our inputs. Now just to show you, I'm going to kind of jump ahead here. I'm going to go to program, main routine. I'm going to put in a couple instructions, and I'm going to put in addresses. We'll just grab 2. You see, local 1 I data 2 is an alias for local 6. This is your wild and crazy I/O that you have instead of what we're using in the manual. Now going through this is really good because it really solidifies your understanding that these tags, these are just arbitrary alphanumeric characters with delimiters that I put in there. I can't put in colons. It won't allow that. So we used underscores. And we'll do another one. We'll type in local. Now when I type in local, I get anything that's local. So we want our alias tag, and we'll just pick 0. And then over here we want an output, so we'll type in LO. It's type forward. It takes you to the list here, and we know that this is actually slot 3, but we want to pick a bit 0. So you see, they both show local 1 I data, local 1 O data for output, I for input, O for output, like it's in slot 1, but it's really not. So this upper tag right here with the dark blue, that's kind of what you're going to see in the manual, but this is the input that it's really looking at in the hardware. So these are kind of looks like the tags that would come with that IQ6XOW4 in slot 1. Remember, this is all about creating tags that look like the tags that are used in the lab projects. The upper tag is the substitute tag, and it is alias to the actual I/O tag. These are the tags that you use to program with. If you add another instruction here, you're not going to go to local 6i. You're going to go to local 1 I data, then you're going to pick the actual bit. And consequently, it will show you your real I/O that it's attached to. The digital field device simulator, if you have one, is our next subject. Okay, the next thing I had you do was, if you have the digital field device simulator and the nomenclature printed on it shows IN 0 through 5 and OUT 0 through 4, or 0 through 6 if you hook up all 6. I had you create controller tags for those inputs and those outputs, and then alias in them. Now it's created Boolean tags, a tag IN00 of the Boolean type, and then alias it 2, local 6i data 0, and do the same thing for the first 5 bits there. And then here. So the nomenclature on the digital field device simulator, it can be used and create a tag that points to data bits that are anywhere in the chassis. We just picked 3 and 6. If I go to the logic, main routine, and create another rung. So I have you create another rung, same logic, same instruction. And then for tags input 0, 2, see, data 2 up there. Input 0, 0, and input 0, 4. And here we've got OUT, and I could drop down and just pick 0. Okay, these two rungs are identical. They have different sets of tags, but both these sets and these sets point to the same module defined tags. So whether you turn on local 1i data decimal point 4 or IN04, you're still turning on this module defined tag. To further define this, or to bring some more clarity, go to Options, Ladder Editor Display, and turn off Show Tag Alias Information. So watch what happens here when I apply this. See? Something interesting. When we created this tag, see, this is a member of that integer tag. This is 0.2. This is the third bit of that tag. So it says right there, local 1i data decimal point 2, Boolean, tag data type integer. But alias 4, that bit is not alias for that whole word, but that's how it's displayed. That's because we did it as an integer, tag data type integer. Now look down here, tag data type Boolean. So it shows that IN02 is alias to local 6i data decimal point 2. Because we defined it at the Boolean level, it shows this alias directly to that bit in that data word. Whereas here, it indirectly goes to that bit through the whole word, because the whole word is aliased. This gives you a format that you can use if you have the digital field device simulator and you want to use that nomenclature instead of actual I/O. Furthermore, let's make this a little bit more complicated. Let's add some more modules. Let's add an IQ, and we'll make it a IQ32. Just put in a fictitious name because I really don't care. Okay, so that gives us a 32-bit card, and then let's, it went in slot 1 because it didn't pick it, so it went into the next available slot. And we'll do an OW 8. Okay, now we have inputs in slot 1 and outputs in slot 2 in addition to these two cards. So now I'm going to go back and I'm going to really mess this up. Let's say that you have inputs and outputs scattered all over the place. They're not contiguous. They're not in order. We'll go and we'll alias this one for inputs in slot 1, and we'll say the lowest numbered one in slot 1 is 9, and then we'll do a couple more here. Well, we can change the slot number here to 1, and we'll just make this just for grins 4. Now when we go back to our code and we want to go to Options, Display, Show Tag Alias Information. Now look, input 2 is now bit. We'll change this to 1. We'll change this to 1. Now you see, this is alias for slot 6, bit 1. This is aliased for slot 1, bit 4. These tags, IN01 through 05 and OUT00 through 03, They can be aliased to inputs and outputs scattered all over the place. It really doesn't matter. Anyway, I hope that wasn't too confusing. Understanding the tag database and aliasing tags is really, really highly important. We are still lecturing on input outputs, I/O modules. With the older platform, Studio5000 RSLogix, I/O was not as vast a subject because there was not the variety available that you have with the Logix engine. And because, as we mentioned before, we have to try to fit this learning collateral to whatever hardware that you have, we're spending a lot of extra time speaking of I/O. Let's get back to the basic format of the basic venue for this manual, and that is a compact Logix processor with an IQ6X-OW4, which is a combination I/O module, 6 digital inputs and 4 digital outputs. In the lab, I had you open the controller tags, expand the module defined tags to make the comparison between these classes of objects, and this is the instance of that class of objects. So local :1:C is an instance of that class of objects, that data type. Then I had you expand to look at the members of that. And by the way, if I double click on one of these classes of objects, it brings up an uneditable, or rather it brings up a view of that data type that you cannot edit. These are module defined data types. They are created by Rockwell Software, Rockwell Automation to support the I/O modules. So you cannot edit this data type. You cannot add to it or take away from it. But by double clicking on any of these module defined data types over here, you can see the structure for that data type. Remember, if you want to close something you've opened here, you go up to this X in the upper right hand corner and click to get rid of those. We don't want to leave those up. Then I had you expand the data for the inputs and then the data for the outputs. And what we discussed was specifically the relationship between the field device and these locations in memory. Now, just in case you've forgotten, these are all locations and memories of this data type. Local :1C, which is an instance of this data type, has 24 bytes of data, which is an integer, 4 single integers, and then of course a Boolean. A Boolean is going to take up at least a byte. You cannot isolate a single bit in memory and separate it from the memory array. Typically with the Logix engine, 32 bits is the minimum allocation or isolation for data. So here we have 1, 2, 3, 4 integers. These are single integers, so these are 8 bits. I'm going to cancel that to get rid of that and get back to here. The screw terminals on your I/O module, and in the manual we have a photo with callouts to clarify this. This location in memory, local :1:I.data.0, that bit in memory represents the state of the input field device that is connected to that screw terminal. Hence, 0 through 5, these bits in memory represent the state of that screw terminal, whatever you have connected to that screw terminal. If you have nothing connected to that screw terminal, then the state of these bits is going to be 0. If you have a toggle switch connected to one of these screw terminals, 0 through 5, and that toggle switch is on, then that bit is going to be on. Consequently, these first 4 bits down here, local :1:O for output, .data.0, whatever is connected to this screw terminal, when the logic turns that bit on or sets that bit to 1, or if you directly from the keyboard, from the monitor mode, which we will do later, but I will expand that out for you right now. so you can see what it looks like. I can go in and change the state of that bit memory to 1 by selecting it and typing in a 1. If this program were online, if this project were online, downloaded to the controller, and the controller were in the run mode, that 1 that I just put in that memory location influences the state of that screw terminal that it represents, which means that that I/O module would have applied voltage to screw terminal 0, and if there was something hooked to that screw terminal, like a solenoid valve or a light, it would energize. With inputs, you have to have something connected to the screw terminal to get a 1, because these reflect the state of the field input devices. The field output devices, their state is not reflected by these bits. Rather, these bits control the state of those output field devices. This that we've just looked at here is what you have to work with if you're using the IQ6X OW4 digital combo module. However, if you're not, then you might be using 2 separate I/O modules. So we bring up another instance where we have a separate input card and a separate output card. If we open up the controller tags and look at those, slot 1 is an input card. Expand the data. These 16 bits right here in memory reflect the state of any input field devices connected to the screw terminals marked 0 through 15. Consequently, the output card, these screw terminals reflect the state of bits in memory. So these bits in memory up here for inputs, they reflect the state of the input field device. In this case, the output field device down here connected to these screw terminals reflects the state of the bit in memory. The state of these bits are controlled by the input field devices. The state of these bits control output field devices. If you're doing the lab projects in this manual with this configuration, a separate input and output module, the first 6 bits here, 0 through 5, are the memory locations. They're the memory locations that you will address with your instructions. Consequently, for outputs, these are the 4 memory locations that you will address with your instructions. And then we have one more variation that we went through, and that was the fixed I/O L23E QBFC1. Now in this case, this has built into it 4 I/O modules. But again, you have an IQ16 and an OB16. So if we look at the controller tags, you're not going to see any difference between this address here for inputs and these addresses for outputs than you did back here where you had an IQ16 and an OB16 as separate detachable, attachable modules to the L35E processor. So remember, we have 3 formats here. The first one is the combination module. These are our 6 inputs and 4 outputs, and that's actually all that you have screw terminals for. There are no screw terminals that you can connect input field devices for 6 and 7. Remember, there's only 0 through 5 and 0 through 3. However, this configuration is a L35E. It could be an L31. That's not relevant to the discussion here. But the point is, we have 2 completely separate I/O modules, each with 16 points. But in the labs, you would be using 0 through 5 of this data and 0 through 3 of this data down here. And then in the third example, which by the way does not really look any different than the second one. The second one, we had 2 separate modules that were detachable or attachable. With the L23E, we have the exact same 2 modules, more or less, but they're built right into the plastic. In other words, the circuit cards are permanently embedded into the plastic housing of the processor. Next in the manual, around page 70 or so, we showed a 4th example. That was the L71 ControlLogix. So we have an L71 ControlLogix. We have an IB16 and an OB16. In other words, we have separate input and output cards. We open up the controller tags and we go to the input module in slot 1, expand the data, and now you have 32 bits. However, because this is a 16-point card, that card only has screw terminals for 0 through 15. The other 16 bits of that data word are unused. For the lab projects, you will be using 0 through 5. Local 1 I data 0 through 5. So again, you see this doesn't look any different than if we go back to, say, the L35E using separate input and output cards, IQ16, OB16. See, local 1 I data 0 through 5. If we go back to the L71 RSLogix, it looks identical. If we expand the data for the outputs, we're going to use in the lab projects local 2 output data 0 through 3, which looks no different than this case where we have a separate output card but with compact logics. It is still local 2 output data 0 through 3. It's really, if you're going to use hardware other than what we use, because we picked the least expensive and the easiest to acquire hardware that we possibly could. If you're going to use something different, the onus is on you somewhat to make the correlation between the memory locations that we point to in our lab procedures and the ones that you actually have. And we've shown you several methods to circumvent any confusion. That wraps it up, I think, for I/O discussion. We used up quite a bit of manual on discussion of I/O, not time wasted, because if you're going to work with a Logix engine, you're going to be exposed to a lot of different I/O types and constructions. Thank you for watching.